let's take a look at how you might have solved the inheritance problem. Recall that in this problem, your task was to write a program to simulate the inheritance of blood-type genes for multiple generations in a family. And the first step was to write a function to create that family, to allocate memory for all of the people in that family, and to inherit all of the blood-type genes from parents to children. So let's do that. Inside of the createFamily function, the first thing you wanted to do was to allocate memory for a new person. So here we called malloc, allocating enough memory for a new person, and saving the returned pointer inside of p. So p is going to be a pointer to that new memory that we have just allocated. Then we need to handle two cases. One where generations is greater than 1, meaning this person we've just allocated has parents. And meanwhile, we need to handle the case where generations is equal to 1, when the person doesn't have parents that we're going to be representing inside of our program. So let's start with the recursive case, so to speak, the generation that does have parents. What we need to do in that case is recursively call the createFamily function to create those parent family trees. What that means is that if originally we called createFamily in order to create a family with a child with 2 generations of parents, well then we need to generate the parent family trees each with 1 generation of parents. So generating family trees that have 1 fewer number of generations. So here, to create 1 parent's family tree, we recursively call the createFamily function on generations minus 1 fewer generation than the generations we started with. And whatever pointer we get back will be a pointer to a parent, so we'll store that inside of parents 0. And because we need to store 2 parents for this child, we'll do the same thing again. Call the createFamily function on generations minus 1, save the output of that inside of parents 1. Now we've updated the parent pointers for this child so that they have pointers to parents and those parents have pointers to their parents if we're trying to represent more than just 1 or 2 generations. But after we've generated these parents, the next step is going to be to inherit 1 allele from each of those parents. And how are we going to do that? Well, we want to choose an allele at random. How do we access a parent's alleles? Well, we can use this arrow notation to access some field if we have a pointer to a struct. So if we have a person P, we can access their first parent with P arrow parents 0. And once we have that parent, we can access that parent's alleles via P arrow parents 0 arrow alleles. And now recall that alleles is an array of 2 characters. There's allele 0 and there's alleles 1. And we just want to choose one of them at random. And how do we get a random number that's either 0 or 1? Well, one way to do it is to use the rand function, which will give us a random integer, and then use mod 2 to get the remainder when divided by 2, which in other words just tells us if a number is even or odd. If a number is even, then when it's modded by 2, we're going to get 0. If a number is odd, then we're going to get 1. And so the effect of this is that half the time we'll get a value of 0, and the other half the time we'll get a value of 1. And this has the effect of randomly choosing one of those 2 alleles from the parent that we then need to store inside of the child's allele array. And how do we access that child array? Well, the child is this variable p here, and they are a pointer to a struct. So to access their alleles, I can say p arrow alleles, and then we'll go ahead and store inside of p arrow allele 0, 1 randomly chosen allele from the first parent. And then we'll repeat the exact same thing for the second parent. Inside of p arrow alleles 1, we're going to store 1 allele from the second parent as well, using the exact same logic, using rand mod 2 to get us a pseudo-random number that is either going to be 0 for the first allele or 1 for the second allele. So that's the case where a child does have parent data that we're going to try to generate. But ultimately, anytime we're dealing with a recursive function, we need a base case, some point to stop, to make sure the function doesn't just keep running infinitely. And so in that case, this is what the else is designed to handle, an individual that doesn't have parent data represented inside our computer program. So in that case, if we don't have any parent data, then both of these parent pointers should be set to null. We'll set parent 0 equal to null and parents 1 equal to null as well. But we also need to specify alleles, blood type alleles, like A or B or O, for these people as well. And if they don't have parents from which to inherit that allele data, we're just going to generate a random allele as part of this simulation. And to do so, recall that we gave you this random allele function, which would randomly give you an allele. So we store one random allele in allele 0, and we do it again to store in alleles 1. And that then is the create family function, the function that is able to create a family tree of a specified number of generations by taking advantage of recursion to generate parent data and then inherit from those parents particular alleles into the child chosen at random. But after we've allocated all of this memory using malloc, we need to make sure that we free that memory when we're done with it. And that's where the free family function came in, which was the last part of this lab. The first thing you needed to do here was to handle the base case. If the input to the free family function is null, then there's nothing our function needs to do. There's nothing left to free, so we can just return. But now we can go ahead and free the parents, because the parents might themselves have parents that need to be freed, that might themselves have other parents that need to be freed. So we are going to recursively call the free family function on the first parent of this person, and then recursively call the free family function on the second parent of this person as well. And that is going to induce even more recursion all the way until we get to that base case, until we get to the last generation that doesn't have parent data, meaning both of the parents are null, at which point this function returns without any additional recursion. But after we freed both of the parents' family trees, all of the parents and ancestors on one side of the family, and then all of the parents and ancestors on the other side of the family, the last thing we need to do is free the pointer for this last child that we dynamically allocated memory for via malloc by calling the free function and then passing in as input this pointer p to free this last piece of data as well. Once we've done that, we will be able to allocate memory for all of the people inside the family tree, simulate their blood types and print them out, and then free all of that data at the end. My name is Brian, and this was Inheritance.